All right, let's look at higher order derivatives. It says find the first and all higher derivatives of p of x. Well, you certainly know how to find the first derivative. The first derivative would be p prime, and I would simply do the power rule. So I have negative 8x to the third plus 27x squared minus 10x. And because that's so much fun, let's take the second derivative, which would be the derivative of the derivative. So the notation is you have, it looks like f, or p, I guess, instead of f. It looks like p double prime, and you would have the derivative of the derivative. So I just get to do the power rule again. So I'd have negative 24 x squared plus 54x minus 10. And the fun can just keep continuing. I can find the third derivative. So it says find all higher order derivatives. So it's like, when do I stop? We'll see. Third derivative, negative 48x plus 54. The fourth derivative, I've usually after 3, yes, I've seen it with Roman numerals, but I want to switch to this notation as well. I've seen it both ways. Usually after 3, they just put the number there. So the fourth derivative would be negative 48. And finally, the fifth derivative would be 0. Now, I'd stop there because, of course, after that, every derivative after the fifth derivative is going to be 0. So wouldn't it be true that all polynomials, remember what polynomials are, pretty positive powers, all polynomials would eventually get down to a derivative of 0 if I kept doing the power rule. So when? In other words, if I have notice that the degree of this guy is a fourth degree, the degree of a polynomial is the highest power when it's all multiplied out. And notice the first time I get a 0 for a derivative is the fifth. So that means if I had a 58th degree polynomial, the 59th derivative is going to be 0. So that's just good to know. So you can just keep finding the derivatives of derivatives. So if the question says, looking at the second example, find the second derivative of f of x, well, you just say, well, all right, I'm going to have to find the first derivative first. So the derivative of 4 cosine is negative 4 sine. The derivative of sine is cosine. There's my first derivative. So the second derivative, the one that they asked for, is just the derivative of that, which would be negative 4 cosine of x minus sine of x. And there's my second derivative. Cool. So it's not hard. You're just kind of keep going. Then we get to example 3. Find the 97th derivative. Are you kidding me? The 97th derivative. People, if they ask you for anything like that, and it seems like all I know from tweets after the AP exam, there was something about a 26th derivative or something, because everybody was tweeting about it. After the 48 hours, they were saying something about the 26th derivative. So there must have been a question like this, and here's the deal. If they ask you beyond like the third derivative and really even just the second derivative, there's got to be something. They do not expect you to do this 97 times. So let's see what's going on. This is going to happen. It's going to end up being a cycle. So notice the question in example 3 is the same as it was in example 2. So I'm not going to sit there and rework the first and second derivatives because they're sitting right here. Had I not started the problem, then I obviously would have done it, have to do that. But I say, if they're asking me the 97th or the 20-something derivative, there's got to be a pattern. I just have to find it. So let me keep going. Let's find the third derivative. That would be 4 sine of x minus cosine of x. So I just took the derivative of this one. Now let's find the fourth derivative. And that would be 4 cosine of x plus sine of x. And at that moment right there, look here. Our original was the same as the derivative. So in other words, if I took the fifth derivative, wouldn't this guy be the same thing as the fifth derivative? And this guy would be the sixth derivative, and seventh, and eighth, and ninth, and 10th, 11th, et cetera, et cetera. I don't have to count. But I think you get the idea. So how do you tell what the 97th is? Well, let's divide 97 by 4. Because if it went in evenly, it would be this one. But if I divide 97 by 4, that's 96, and I have a remainder of 1, which means the 97th derivative, when I get to 96, this would be the 96. This would be a remainder of 1, remainder of 2, remainder of 3, and this would be kind of go in evenly. So since I got a remainder of 1, when I divided 4 into 97, then the 97th derivative is going to be the same as actually the first derivative, and I get this. So if there is a high order, like a really high order derivative they ask you for, look for the pattern. Keep finding the derivatives until you get back to the original, because you will, and then just find out the cycle, and you can get that derivative. All right, let's look here. So we have a position function of an object, and we kind of already talked about this first one. The rate of change of position with respect to time is the velocity. And here's the new part. We said that velocity is the first derivative of position, is what we have, and we've already figured that out. But now, since we can take higher order derivatives, that the acceleration, I could say it two ways, is the first derivative of velocity, or the rate of change of velocity with respect to time, or the second derivative of position. And then, this is just a good thing to know, because we'll get to that. We'll get to that part in just a second. But whether it's speeding up or slowing down. So let's just work with a little bit, and then we'll go to that statement. So it says, assume an object moving along a line is given by, I can read, that equation for t being 0 to 8. Find the beginning position. Well, the beginning position, so a lot of these things are just interpreting. So beginning position, that would be s of 0, so that's really all you'd have to label, being that all of these things have a t in there. If I plug in 0 for t, my answer is going to be 0. So it's actually like at the origin, if you want to think of it as on a number line. Find the velocity at t equals 2. Well, you know that the derivative of position is velocity. So all I have to do is look at this position equation and take the derivative. So power to the front, that's going to be 9t squared minus 81t plus 162. Now, that's not what it asked me for. It asked me for velocity at 2. So once I have that, I'm just going to plug in a 2 there. So 9 times, I think you can follow me, 9 times 2 squared would be 4, that'd be 36. 81 times 2, 162, plus 162, that works out nicely. So I get V of 2 equals 36. Notice my labeling, okay, how I label everything. Now, this did not say anything about units. Units were not introduced in this problem, so I do not have to put units on my answer. I don't have to say units over time squared or whatever the case may be, units over time. If they didn't introduce units, you do not have to put units in your answer. But you do need to label V of 2 equals. Okay, find the acceleration at t equals 2. Well, acceleration is the derivative of velocity. So I have the second derivative of position, or the first derivative of acceleration, is a of t, and that is equal to 18t minus 81. Now, I'm not saying that you have to write this part. If you went straight to a of t is 18t minus 81, they'd give you credit. I'm just writing that since it's our first time to talk about it. So you kind of get it in your head. Acceleration is the first derivative of velocity, or the second derivative of position. And likewise, I can put a of 2, and that would be, what is that, 36 minus 81. So I have a of 2 being negative 45. So that's my answer for part C. Then we have part D. Is the object speeding up or slowing down at t equals 2? One of the biggest mistakes is this question right here, because when they say speeding up or slowing down, you tend to think in terms of the velocities that you're thinking about, like speed of a car. And so velocity, of course, is always positive. You're kind of thinking of it that way, and so it messes you up. And you look and you say, well, the velocity is positive, so it's speeding up. What you have to remember is that velocity has a direction assigned to it as well. And so if a particle is moving along a line, that particle could be moving to the right, or it could be moving to the left, or it could be moving to the right or left and be going back and forth. So there is a direction with the velocity. And you have to know that this velocity right here could have been negative. And so here's where this statement comes in. An object is speeding up if the velocity and acceleration have the same sign. An object is slowing down if the velocity and acceleration have opposite signs. So the key is, when they ask you about speeding up or slowing down, write really big somewhere on your notes, you have to look at both velocity and acceleration. You cannot just look at velocity, and that's what people tend to do. They say v of 2 is positive 36, so it's speeding up. And that's not correct. And even if it was speeding up, they would not give you credit because you don't have the right reason. So notice they actually ask you at t equals 2, which is nice because we already figured that out. You figured out that the velocity at the velocity at 2 was 36, positive 36, and the velocity at the acceleration at 2 is negative 45. So I would say since, and I've labeled this and shown this, since v of 2 and a of 2 have opposite signs, the object is slowing down. Because if it's accelerating in the same direction that it's moving, then it's going to be speeding up. So if you think of something being dropped from a building, well, the velocity is going down and it's accelerating. So if you drop a penny off of a building or something, it's speeding up when it's falling. And so that's why if they're both the same sign, even if it's negative, it is speeding up. So there you go. Work the homework and let's see how you do.